Okay, dear students, welcome back. We are here at the Masters in Bioethics, the course in Environmental Bioethics, our last lecture of this course, beginning always with a little prayer. In the name of the Father, the Son, and the Holy Spirit. Come, Holy Spirit, fill the hearts of your faithful, kindle in us the fire of your divine love. Amen. Father, Son, and Holy Spirit. Okay, before proceeding, any questions or comments from previous lectures or anything in the program? Yes.
First, about the program, when are the internship hours due?
Yes, they will be due at the end of November, all right? Because then so the internship is only pass-fail, right? There's no grade on it, but it's pass-fail. And I have to turn in that grade by December, the second week of December, but I want to give myself a little margin there, all right? So end of November.
And my second question was, last time you were talking about how in nature there's a lot of clustering.
Yes.
Natural. Can
Yes.
you elaborate a little bit on that, like how?
Yes. So that has to do with distribution, geographical distribution that is either homogeneous or heterogeneous, basically, all right? And homogeneous would be spaced out, for example, right here in this classroom, the desks and the chairs are somewhat homogeneously distributed, right? So there's more or less the same even space between them. But that's not the case in nature. Generally, the standard in nature is clustering of individuals, whether we're talking about plants or animals or fungi or bacteria, okay? So for example, I can tell you with the slash pine, since you've been working at the forest, the baby pines, the volunteers, the seedlings that come up, typically they're not distributed homogeneously, but rather they come in clusters. So I say, if you find one, keep looking because likely you'll find another one around it, around that one, all right? And one pattern that is typical of trees in general in forest is that the seedlings of the next generation are on the periphery of the canopy. And we see that phenomenon, for example, you look at the core sector, what I'm calling the core sector, right? We have all the baby pines flagged. All right, if you notice the pattern there, you can see it very visually. All the flags are around the periphery. And if you look up, it's the edge of the canopy being the highest part of the trees. And typically the canopy is defined by the dominant species, right? Which in our case is the slash pine. So there are very few seedlings that are coming up in the middle of that cluster of those 20 pines. The 20 adults are there. Most of the new ones of the seedlings are on the edge. So with your mind's eye, you can push that forward 20, 30, 40 years from now as those seedlings become adults. And the older ones eventually will die, right? Because their lifespan is 150 to 200 years. They don't live forever. So eventually the adults that are at the core will die, all right? And if we leave them there, they eventually will rot and fall off over a period of years. So the new layer is the outer layer. When they grow and become adults and they put out their cones, the next generation of seedlings will come out on the new periphery. And so it's a gradual opening, a gradual expansion. So basically it will leave the forest alone, taking out the invasives, right? So that the forest now has space. It will reforest itself. It will reforest itself but it will take decades. It's a slow process, okay? But the forest will reforest itself, right? As long as they have enough space where to grow. And that clustering is a typical pattern that occurs both animals, plants, fungi, also mushrooms, and even bacteria.
But is it, I don't know, but I feel like
Yes, there is, exactly. And that's exactly what it is in nature, is competition. There's no getting away at the, excuse me for a moment. Okay, sorry. Yeah, Chris is held up at the gate. Let me just say, have them call me. Yeah, sorry. Exactly. So there is competition for sure. And so a couple of things about the competition. First of all, the distance between the individuals is crucial, not only in animals, but also in plants. And each species knows what is the proper distance to keep, right? So that they don't eat each other or they don't overcrowd each other. For example, with the trees and vegetation in general, they're all competing, the individuals are competing for light above on the shoot and for water underneath the ground in the root system. So there's a specific distance between individuals of each population. And each population knows that, each species knows what that distance is. You know, we can only observe it, but they know that distance that they keep. And then there will be competition, so that in general, if you remember from natural selection, in general, on average, the strongest will survive, the more fit. But the fitness is not physical fitness, right, of muscle, because, for example, trees don't have any muscles. It's genetic fitness. We can see it also with the pines now. The seedlings that have drought resistance remain green through the winter time. Our winter, November, December, January, February, for about 4 months at least, there was practically no rain. And these pines, they love rain, you know, they love water. So there was no rain, and that was a clear distinction between the seedlings that had the drought-resistant genes and the ones that did not have the drought-resistant genes, or those genes did not express correctly. They dried out, they died. And so you see that nature is always selecting that way, you know, but it's a blindfold selection. It's not a directed selection. There's no thought to it, all right? It's just random. Whoever has the fitness genes, they will survive. Sure. Yeah, so this thing of clustering, and we can see biologically, it's interesting to look at the human species every now and then also from the biological perspective. From the biological perspective, in that we follow a lot of the pattern of other species, right? Especially mammals. It's just that because we're so sophisticated about it, many times we don't realize. So we're following very much things that in other animals are instinctive, like, for example, the clustering or the herding, okay? That's typical of mammals. So how do we do herding? In cities, precisely, in cities. And so there's a natural attraction for people to come into the city to the point of overcrowding. And like I mentioned last time, the extreme dramatic example of that is the megalopolis, all right, where we find most of the social issues, social difficulties. In fact, talking about COVID that we were talking about before the lecture, you can see that where is there going to be more selection? I mean, COVID, if you think about it, the coronavirus is doing selection on the human population. And on average, who are the ones who are getting infected and who are not surviving the infection? On average, the weaker ones, the less fit, the ones who are overweight, or they have a comorbidity, or their immune system is compromised for a number of reasons, right? So just on the purely natural aspect of it, they're being selected out, okay? So in a very dramatic way, in 2020, we saw a very clear example of natural selection on the human species. In spite of all the technology that we have and the practice of medicine and all this, right? So when we have extreme cases like a pandemic, this is the first true pandemic that has occurred, as far as we know, in the history of humanity, that has been truly worldwide, all right? So a lot of natural selection went on last year, and yet with our minds, we were able to try to minimize that impact as much as possible. Besides the vaccines, before the vaccines, with the distancing, with the quarantine, the mask, but especially with washing of the hands, that's been the most effective means of minimizing the propagation of the virus. Okay. All right, so let's go forward now. And this lecture really is kind of the culmination of everything that we've been looking at in environmental bioethics so far in the other 5 lectures, which, as you can see, has been both abiotic factor and biotic factors, right? When we looked at the formation of the Earth first, geosphere, hydrosphere, atmosphere, those are all abiotic. And then the distinction between climate and weather, which is very relevant now for this particular lecture, energy, and finally, last lecture with population growth, including the human population, all right? So now we're gonna look squarely at climate change itself. Is there climate change? What kind of climate change, right? And then the consequences for that for our humanity and in the environment at large. So again, we're going to make some distinctions here with regards to climate change first, and some of the other consequences, global warming, ice melting, sea level rise, the acidification of the ocean. And then loss of biodiversity, which is not necessarily driven by climate change, all right? Because we're seeing a dramatic loss of biodiversity. In other words, there is a background extinction rate that is occurring all the time. Keep in mind that every species that exists or has existed, its fate is to become extinct sooner or later, all right? So no species has lasted. Maybe the few species that have lasted for millions of years would be archaea or bacteria, all right? But all other species that have come up in the plant and animal world eventually have become extinct, and then new species have come forth in the evolutionary process. So we need to look at the extinction rate and what's happening now with the acceleration of that extinction rate. Then our footprint, meaning we have to live somewhere, right? So that's the challenge. We do have to live somewhere, and whenever we live, because we are accustomed to living, sheltered from the environment, we no longer live for the vast majority of the population just under the tree or in a hut or something like that, then that's going to have an impact wherever we are. Okay, so let's go forward then, always with the big picture first, just to recall that just in the past 500,000 years, we've had 4 ice ages already, 4 glacial and interglacial periods, all right? And this has been going on for a long time in history. This other scale is expanded further to 2.5 billion years. So that's about half of the world's existence. But even in the past half billion, there was another, let's see, we would be in here, because this is a large scale. The past 500,000, there's another cycle of ice ages, right? And what does that mean? It means that climate is changing all the time, just like weather is changing, but weather changes on a daily basis, up to an annual basis. For example, when we have seasons, right? So weather is changing all the time. It's a dynamic system. with the accumulation of weather over a long period of time, eventually we do get climate change. Sorry, do you mind closing the door there? All right. So climate change is long-term, and typically climate change is measured in geologic time. Geologic time is at least thousands, hundreds of thousands of years, or millions of years, really. All right. So climate change is long period of time. And we just haven't had thermometers out there in the atmosphere or on Earth to measure climate change directly. All right. So a lot of the measures are done indirectly, getting a little bit ahead of myself here, but the indirect measures are done mostly by ice cores, and we'll get there. Anyway, just to point out that it has been a lot of climate change in the history of Earth. A lot of climate change with which we had absolutely nothing to do, because it's even before the human species existed. And even after it existed, we just didn't have the power to affect that climate change. We weren't producing that much CO2 in a significant way, because it's only since the industrialization age, the past 200, 300 years, more or less, all right? So these are some events that influence climate change significantly. For example, the Earth's orbit, all right? In other words, going around the sun 1 year at a time, that's called the eccentricity, all right? Or the translation of the sun around the Earth, the Earth around the sun. Also the angle of, you know, that our Earth, the axis is angled, right? And that's called obliquity. That also has an effect on climate change over long periods of time. And also that axis is not, the Earth is not rotating exactly around the axis. The axis is actually wobbling a little bit, right? Wobbling. So for example, I know if, when you were kids, you played tops. When I was in school, we used to play the top, right? ¿Cómo se dice en español? El trompo, the top. And when it's spinning at high speed, it's right on the point, and it's pretty much on edge and right rotating around its own axis, all right? But we start losing speed little by little, it starts wobbling, okay, until eventually it will fall. What makes the top lose speed, by the way, what is it? Believe it or not, is the friction of the point on whatever surface it is, because it's almost down to the microscopic level there. Typically the tops have like a steel point, right, or an iron point, like a nail or something like that. But it's on the asphalt or concrete, and as tiny as that contact is, there's still roughness at the very local level. Okay, so it's an uneven surface, both. And so there's a lot of friction there. We could measure it, it'd be heat release because of the friction. And that is what slows down the top part of it. The other part is the resistance that the wind is offering, that the air around it. It's also causing some friction, but eventually the top will fall off and it will wobble like that, right? Well, so our axis is also wobbling a little bit, okay? Which means that at some point, if that wobble continues to increase, that may also send the Earth out of its orbit. And it's anybody's guess if it will send it out through the centrifugal force, leaving the solar system into space, or the opposite force, centripetal force, which will be essentially the gravity of the sun, which will pull us in to collapse into the sun. Either way, it's a dramatic end. So it's estimated to be several 100,000 years, or if not millions of years away. So if we see it, we'll see it from upstairs somewhere, okay? But these are things that influence climate change, right? Also, on the Earth itself, the tectonics and continental drift, if you think about it, precisely because those continental plates are still moving around and shifting around, all right, that crust is not homogeneously distributed on the surface of the Earth. It's rather lopsided. And at this time, in our particular time, the landmass, the crust, is mostly on the northern hemisphere, right? Because the south is mostly oceans, except for the tip of South America, Africa, and India, and then Australia. And then, of course, at the southern pole, you have a whole other continent there, another plate, which is Antarctica. But it's heterogeneously distributed. That also makes the top rotate a little unevenly because of the uneven distribution of masses at the surface, all right? So that can also cause climate change in these long cycles. Volcanic activity also, because when there's volcanic activity, all of a sudden within a very short period of time, which can be just days or weeks or months at the most, there is a huge amount of CO2 and ash and even methane, other gases that are all greenhouse gases spewed out into the atmosphere all of a sudden, and it wasn't there before. So that can also trigger like a tropicalization, right? So all of these events, we have no control over them, and all these have impacted the climate so that all these have produced climate change. The big question then is the anthropogenic climate change. In other words, generated by humans. Anthropos, reference to human, genic, generated or initiated. So the anthropogenic climate change is what we're concerned with. Chris.
How much volcanic activity is needed to actually affect Earth's climate?
Okay. It's not known exactly because we have to go by what's happened already. But we know that there is a gradual cooling of the Earth, right? Remember that the Earth used to be first just a molten ball of lava, essentially, when it was accretion, right, was coming together. So gradually, over the billions of years, we've been losing heat to the universe, which is entropy, heat that is unavailable for work. And so bottom line is that the Earth has been cooling down little by little, and the crust has formed, right? Once the crust forms and solidifies, it becomes more stable, but the plate tectonics are still there. What I'm trying to say is that going back in geologic time, there used to be much more volcanic activity. In fact, at some other time, I've mentioned that the atmosphere itself, the composition of the atmosphere has changed about 4 times. And early on, it was much more toxic, much higher concentration of CO2 and methane and other gases that would be totally toxic to us, you know. And it was thanks to the cyanobacteria that started producing a lot of oxygen and consuming CO2 precisely in the photosynthesis that changed the atmosphere, changed it drastically so that we could have the life that we know on it today, all right? But the volcanic activity has been subsiding little by little, all right? And today, the volcanic activity that we have is practically nothing compared to what it was a few million years ago, because it was volcanoes all over the place when the plates were shifting around, all right? So whole ranges of volcanoes firing up. So yeah, that was pretty drastic, and that also tells us that the atmosphere was not as stable as it is today. Right, with the gases that we have and the composition that I told you. The atmosphere was more in a dynamic state earlier on, just as the Earth itself was in a dynamic state as it was cooling down. Yep. Mm-hmm.
I understand the precession, I just don't understand why. Like what makes it wobble? Is it heavier on one side?
Yes, the shift. So you think probably the most stable of the layers, so we have 5 layers, right? Beginning, we have 2 cores, we have 2 mantles, and then we have the crust. And of those 5 layers, I would say that without being a geologist or anything like that, the core, the inner core, is probably the most stable, which is a solid ball of iron and nickel. All right, the 2 most abundant elements on Earth. And that's solid and it's white hot. So I would say that that core within itself is pretty homogeneous. It's just a gigantic ball of metal, of solid metal, of iron that is extremely hot, all right? But that core is probably fairly homogeneous. So it's pretty much a nice round ball. But then you have the outer core, right, which is liquid. So liquid now can shift, all right? And there may be some heterogeneity within that layer. Then you have the mantle, which is molten lava. But again, they could be more dense on one side, less dense on the other. So that's going to make that spin a little different. Okay, all that is contributing to the wobble itself. All right. So here we have, this is the other one that was mentioned aside from these big, huge cycles that we have measured in billions of years, all right, there are also these shorter cycles within 500,000 years. Okay. We have a little more information about this one. So you can also compare the two curves. For example, see how smooth this curve is, because it's not as much detail. You had the statistic scores. There's less data for this. All right, so it's a smoother curve. But this one is more jaggedy. We call that noise in general. You can still draw a slope. If you were to draw a slope here, you would get basically 4 bumps and 4 dips, right? Notice where 0 is centigrade, so that's freezing, above freezing and below freezing, right? So this, for example, would be an ice age. This would be a glacial period. This up here would be interglacial, glacial, interglacial, glacial, interglacial, glacier. And now we are hovering around 4, around 0 centigrade. Okay. And you can see that the ice volume matches up with the same contour, 500,000 years. So basically that is telling us that the Earth has gone back and forth between what we call a winterization, where we have glacial periods, most of the continents covered by ice. And when I talk about ice, I'm not talking about 5 or 10 feet of ice. Talking 1 to 2 miles of ice. You know, it's just amazing. It's hard to imagine 1 to 2 miles of solid ice on top of the continents that, by the way, are also moving back and forth like this over the thousands of years as ice accumulates more at the top, at the poles, and pushes, the pressure pushes down again because of gravity and so forth. So at the bottom of those glaciers, at the surface of the Earth, they're grinding back and forth. Nothing lives down there. Okay, everything becomes barren. Even the soil that's displaced is down to the barren rock. And I can tell you that the Great Lakes of the United States, right? Let's take a photo, just a satellite image. The 5 Great Lakes that are between the US and Canada today, right? They were carved out by glaciers, all right? And they're some of the deepest lakes in the world. You can see a little bit, using a little imagination, they're kind of like a hand like that. 1, 2, 3, 4, 5. Sorry, Huron is here, Ontario and Erie 5. So they were carved out by glaciers moving up and down on the rock there, all right? Some of the deepest lakes are V-shaped like that, very, very deep. So that's the power of glaciers. Providentially, the glaciers never came down into the peninsula of Florida. So the peninsula became like a refuge, not only for animals that kept migrating forth in the front of the glacier, but also plants, because these processes took thousands of years, which means that it gave the opportunity to plants to put more progenies forward, and when those grew, put more progenies and so forth. So some plants stayed ahead of the glacier, but also it was a winter environment. So that's how we got the conifers here. That's how we got a slash pine, because pines are conifers and they typically live up north. For example, up in Canada, Siberia, all that are coniferous forests. So what is a slash pine doing down here in a subtropical environment? It adapted during the last ice age, which receded about 10 to 12,000 years ago. But the peninsula itself was never covered by ice. So this became a refuge of all kinds of animals and plants. We had the large mammals. We had the saber-toothed tiger here, that huge thing with the fangs. We had giant sloths and all those prehistoric animals down in the peninsula, right? Then on the opposite side is when the poles melt and we have a full meltdown and there's no natural ice left on Earth, all right? When we go on these peaks here, all of the ice melts naturally. What happens is all that water needs to go somewhere, it goes into the oceans and it rises the sea level. And the average rise of sea level in a full tropicalization, what we call tropicalization of the Earth, where the poles are totally melted, meaning that the North Pole disappears because that's basically an ice cube, right, that's sitting there. And the South Pole, Antarctica, becomes barren rock and soil because it loses all of its ice. The sea level will rise an average of 100 to 200 feet above the current level. Now, right now, we're all aware of the peninsula where the coast is, the East Coast, and then Naples, Marco Island, Tampa, all that on the West Coast. The average height above sea level here in South Florida is about 6 feet, all right? Average height above sea level. So it's very flat. You put 100 to 200 feet of seawater on top of us, we're totally underwater. So the peninsula used to be a coral reef. And that's why we have sand here and shells. You find all kinds of seashells here in the forest, all right, and sand. Now, were there trucks? Did people bring trucks of sand into this area? Absolutely not. We're, I don't know, maybe 4 or 5 miles away from the coastline today. But back in the last tropicalization, we were underwater. Okay, and these are natural cycles of which we had no influence.
So what kind of life would survive in ice?
It depends. On the ice itself, nothing, all right? Or underneath it. Maybe some bacteria in suspended animation, frozen, okay? Some bacteria frozen, or maybe some microorganisms that survive a freezing stage. But everything, so basically the lower edges of the continents, right, the southern boundaries of the continents remained without ice, and that's where all of the vegetation and the plants and the animals were living. But also keep in mind, because of all that ice in the glacial periods, that water to form that ice had to come from somewhere. It was the evaporation of the oceans, the cycle, and dropping of snow on top of on the continents. So the sea level was lower, right, by maybe 100 to 200 feet. And it also means that there was more coastline available during the winterization. So there was more exposed land, okay, during the winterization, especially along the coast, the low-lying areas. So it goes back and forth like that. And it is in the larger picture of, again, hundreds of thousands of years into millions of years, there's a cycle, there are cycles going on. All right, but then we have this phenomenon. So we follow CO2 because we know that CO2 is a greenhouse gas, which means what? It retains heat, exactly. And so by retaining heat, it warms the atmosphere. By warming the atmosphere, that warmth is transmitted also to the ice. Basically, the two large chunks of ice on Earth, natural ice, are the two poles. And then the third one is Greenland, right? Which is an island, but it has a huge glacier on top of it. And then the other glaciers on top of mountains, which by comparison to the other three chunks of ice, it's negligible. the glaciers, but still they exist in large mountain ranges like the Rocky Mountains, the Andes, the Himalayas, the Alps, okay? All right, so this is data mostly from ice cores, precisely. And you can see that the cycling of the CO2 matches up with the tropicalization and winterization, the 4 ice ages of the past 500,000 years, all right? But then look what's happened since 1950s. This graph has shot up exponentially, practically vertically, and for the first time, at least in the past 500,000 years, 500,000, right? It went beyond 300 ppm. Remember parts per million? We saw parts per thousand, parts per million. It's a way of measuring particular compounds, either in a liquid or in a gas, all right? For example, salinity typically is measured in parts per thousand, and the gases in the atmosphere, parts per million, because CO2 is a very tiny amount. But that tiny amount has a big impact. So in the 1950s, for the first time in the past 500,000 years, the CO2 in the atmosphere globally went beyond 300 ppm. That was significant because those were the highest peaks that we had, all right, in a full tropicalization. And since then, in the past 70 years now, all right, a little over half a century, it's gone to 400 parts per million, okay? So this, for the climatologists, this is very alarming. And this is what is considered that could be anthropogenic. Anthropogenic because we don't see this kind of pattern anywhere in nature, in spite of the cyclings of winterization and tropicalization that have been occurring. We don't see this kind of dramatic rise at all. And it happens to correlate with the Industrial Revolution, which started by the steam engine, right? And the steam engine, how do we get the steam? By heating up water, boiling water. How do we boil the water? By the fire. How do we get the fire? By burning coal. So there's a lot of sequences here, right, that match up. So this is a website, this is from NASA, and it's a website you can check down here, all right? That's the curve. This is the concern, the anthropogenic CO2 is the biggest one. There are others, methane also. In fact, methane is much more greenhouse, much more retaining heat than CO2, but it's in a much smaller quantity than CO2. It's in trace amount for now. All right, now, speak of statistics. One of the past courses in the statistic was taught by another professor, and we did R. I don't know if any of you have worked with R, but it's a program, it's a statistical program that you can download it for free. And it's very nice because you can do all these different graphs with it. All right, it requires a little bit of coding, but basically you upload the data in an Excel file in columns and rows and so forth. And R, with a little coding, will crunch it for you and will make whatever graphs you want, all right? So I overlaid these 5 factors here. Typically on the x-axis, we have the independent variable, which is time, all right, from 1975. And on the y-axis, just an arbitrary unit so that we have some kind of unit to measure there. And follow the graph. This is population growth since it was about 1980 actually that I found the data, from 1980 to 2010. All right, so that's 30 years. It's a short period of time, but you notice the correlation here. Here's population growth in red. You can see that it's rising. It looks like a straight line here, but if we were to magnify the scale, all right, beyond 30 years, let's say we project it to 300 years, this line will curve and become exponential, which is that exponential growth rate that we saw of the population growth last lecture. Okay, so it looks linear simply because the time scale is small. But if we magnify this, the time scale, it will start curving, all right? And it's just one little segment of an exponential growth. Then CO2, both are positive slopes. Now, at least the good thing about this is that within this small time frame, the population is rising faster than the CO2. In other words, for more people on Earth, proportionally, there is not as much more CO2. There's more CO2, but not as much more. In other words, these two lines are not parallel. The slopes are both positive, meaning they're both growing, but they're not growing at the same rate, all right? So you can look for reasons of why this, maybe because as time passes, we're more careful about the CO2, there are more filters in place, there's more regulation of industry, etc. And so the rise of CO2 has been slowing down. The rise has been slowing down. That's a possible explanation. It's reasonable, all right? But then the other two, of course, are cycling. Temperature. Why is temperature so wiggly? Well, because temperature is going to cycle according to the season, right? Summer, winter, back and forth. So that's why you get the wiggle, but you can still do a slope of the green line and you will get a positive. But notice that that slope, I should have done that, put a slope here, I just didn't want to put too many lines. But if you do a slope on the green line, all right, approximately like that, you see that not only is it positive, it's a pretty sharp positive. It's faster. It's actually a higher rate than the CO2 and the population growth, which means that even just a small amount of increase in CO2 has a big impact on the climate. You follow? So that's something to consider. All right? The temperature of the atmosphere is highly affected by a small increase in CO2. So that's to consider. Then the other one, the dark blue, is sea level rise. Okay, sea level rise. Also, these two slopes, just to the eye, are kind of parallel. As the atmosphere increases in temperature, the sea level is also rising, but that sea level rise is an effect. You know, it's not that just by heating up the atmosphere, that doesn't make the sea level rise by itself, right? There's an intermediate. What is making the sea level rise? But what is the temperature, what is the rise in temperature doing to make the sea level rise? In other words, sea level is liquid, right? What does the sea level need to rise? More liquid, melting the ice, melting the natural ice, melting the poles. So the melting of the poles is what's contributing to the sea level rise, because that ice has to go somewhere. When it melts, it goes into the oceans and the sea level rises. It's like an ice cube, you know. So the final slope is the ice melt. And you notice it's very small, very slight. It's negative, of course, because more ice, less ice, right? So you expect a negative slope on that one. And it's very small, very slight, but that slight melting of ice is contributing to a lot of sea level rise. So it's somewhat similar to the CO2 on the atmosphere. A slight rise in CO2 highly contributes to warming the atmosphere, black and green, and a small melt of ice contributes highly to sea level rise. All right, so these are, it's a little bit like you can think of it as hormones. You know, a small amount has a big impact. A little bit of hormone has a big impact on the body, all right, on metabolism. So these are like catalysts. All right, I have a series of little videos. Well, this site itself, again, from NASA, because it's all dedicated to the scientific evidence for climate change and trying to parse out what is anthropogenic of this. So you can explore it. That's where I got the graph, as you can see, front and center. It's got a number of tabs that you can explore. And then it goes into text of the different, the global temperature, melting of the ice, glaciers melting, sea level rise, especially for coastal cities, and a number of those megalopolis are actually along the coast. More extreme events is, one theory is that the climate change also affects the drastic weather more, all right, an increase in drastic weather like hurricanes and so forth. The acidification of the ocean, we'll look at that in a little more detail further down. It's one little interactive link here that is worth saying. It's just a couple, it's less than a minute, but take a look. This is measuring since 1900, so we started again. 1880s actually. All right, so you follow the timeline here. It's about 100 years of superimposed measurement of heat on the atmosphere, all right? And of course, blue is cold, yellow is warm, red is getting warmer into hot, all right? So you can see here the overlay. Here's the scale in centigrades. And it goes back and forth because of the seasons. So you can see a little bit of the cooling, warming. But the general trend tends to be more yellow and now more red to 2020. So it's pretty dramatic. Those are typical superimposed satellite image or data by NASA. So there's plenty of evidence that yes, that we are gradually warming up. Now, I have a series of videos here on different aspects. The melting of the Arctic. So remember the three big chunks of ice, natural ice, right? Starting with the largest one is going to be always Antarctica because it's a whole continent. Then the second largest, the North Pole, the Arctic Circle, which remember is, there's not a continent as such, so it's a huge ice cube basically sitting there, and it's held in place mostly by northern Canada on one side and Siberia on the other side, right, which tip it to the Arctic Circle. And then in between those two, there's the island that comes down, which is Greenland. We'll look at it in more detail. And Greenland also has a huge ice sheet on top of it. It's a glacier. So those are the three main sources of natural ice on Earth. This one is just, again, a little time lapse on the melting of the Arctic, which is over.
If you're learning guitar late in life, there's one distinction that will determine if you're going to succeed or fail.
Thank you. Okay. Now, I forgot to do the enhancement thing here, optimize. Okay. Here we go. So you see Canada down here. All right. Here's Alaska, the Bering Straits. Here's, sorry, Bering Straits over here, Siberia, all the way into Europe. Here's Scandinavia, all right? Great Britain, Ireland, and here is Greenland, okay? These are actual photographs. This is not painting, this is photograph.
In 1978, satellites began continuously observing the polar regions, and the dynamic beauty of the Arctic sea ice was revealed. What we expect to be a solid mass of ice is actually in constant motion. As researchers continue to seek a deeper understanding of this region, new information about how sea ice changes is coming to light.
This special ice.
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older ice is thicker ice.
That's the voice of Dr. Walt Meyer, senior research scientist at the National Snow and Ice Data Center.
What you see in this animation is the ice pulsing out and in with the seasons. In winter, the ice grows out and expands outward. In summer, it contracts inward as it melts. You see the whiter ice, which is the older ice, moving around the Arctic, being pushed around by winds and currents that move the ice. Over the years, the ice pulses around and moves around towards the top along the coast of Greenland. The older ice eventually moves out of the Arctic and into the North Atlantic, where it melts. The ice gets replenished within the Arctic because some of the ice survives each summer and grows older. And particularly in a region north of Alaska called the Beaufort Sea, where the ice spins around in a clockwise direction called the Beaufort Gyre. And that ice can keep spinning around oftentimes for several years and gradually getting older and thus getting thicker. Eventually, the ice will spin out of that gyre and go out through Fram Strait. In the past, we've always had enough ice growth and ice aging, enough ice surviving the summers to replenish the older ice that's lost. But in recent years, we've seen less replenishment. There's been more melt during the summer, so the ice that goes out through Fram Strait has not been compensated by the ice growth. In addition, especially in recent years, we've seen some pretty remarkable things in the Beaufort Sea, where that area that used to be a nursery for the development of the older ice allowed the young ice to age and mature. What we've seen instead is the ice is now more broken up, more scattered, and that's allowing the older ice to melt within the Beaufort Sea. So we're seeing the Beaufort Sea go from a nursery to a graveyard for older ice. As we get towards the more recent years, much of that oldest ice, the ice that's older than 5 years old and the bright white, has almost virtually disappeared from the Arctic Ocean. And the Arctic is now dominated by younger and thinner ice.
30 years, huh? 30 years, amazing. That's satellite imaging, so there's the evidence. In fact, now they're talking about the Arctic Ocean, where some ships are able to navigate from the Pacific to the Atlantic or vice versa through the Arctic, right? So it's pretty dramatic up there. It's not the major ice cap is Antarctica is the major one, but it's still significant. All right, so speaking of Antarctica, here's one. Yep.
If the greenhouses were to be lessened,
Right, diminish.
would it be recreated?
Right, so it's anybody's guess, but these are long-term cycles. If eventually we get this black line, which is the CO2, to level off so that there's a neutral slope and maybe even get it into a negative slope, right? Then everything else should react accordingly. The green should also follow and transition into a negative slope, right? Thus going more toward a winterization. But this is the big challenge there, yeah, because a little increase here has a big impact on the temperature. All right. So the expectation, just like nature will replenish itself if we leave it alone. All right. It takes a long time. It goes into geologic time. That's the challenge there, that we cannot afford that type of time frame, because what's the generation for human? One generation is considered about 20 years for the human species, which is really, it's a very short time scale, all right, for our species when we compare it to geologic time. Okay, so let's look at this other one, going to the opposite pole in Antarctica.
An NET television production.
And the drilling that is occurring there to determine precisely the ice core. And what they do with drilling, mostly because we don't have thermometers that go back thousands of years, we have to look at the indirect evidence, precisely tracking the CO2. What they do with the ice cores, they go deep, and then they section those ice cores, and they measure the little bubbles of atmosphere and little bubbles of CO2 that are trapped in the ice core. And they're tiny, but we have instruments, science has instruments now that are so sophisticated that can measure the amount of CO2 trapped in those little bubbles of atmosphere, of air, in these ice cores, all right? And they can also tell, because you'll see layers, talk about volcanic activity. Whenever there is volcanic activity, typically if the volcano shoots up high, 5 to 10 kilometers up, within 24 hours, it will go around the world, all right? Because of the jet stream. It will go around. So eventually that ash will deposit throughout the world. And it will be thin, but it will deposit on the ice and will generate a layer, like that can be measured layer by layer. So you get these layers of black and white on the ice. And that's how the core is dated, all right?
Antarctica is the iciest place in the world. There's so much ice here that only a few valleys in all of Antarctica are virtually ice-free. Everywhere else, ice encases the continent. But Antarctica's icy cover is deceiving. Surprisingly, much of this ice is on the move. Antarctica may appear to have a single coating of ice, but not all the ice on the continent is the same. The majority exists as ice sheets that cover the land and slowly move towards the sea. From Land's End, the ice continues to move as ice shelves that extend over the sea. And beyond the ice shelves is seasonal ice that freezes the sea in winter and thaws in summer. Polar researchers use the 3 types of ice to detect how Antarctica affects global climate. 600 miles from McMurdo is the West Antarctic Ice Sheet Divide, the high point of one of the world's largest ice sheets.
We're a mile above sea level, and even though it's incredibly flat, there's actually 2 miles of ice below us. Most people think of this as just snow. My colleagues and I, this is a collection of chemicals and gases that are characteristic of the climate when the snow fell. Now, the snow here never melts, it just piles up layer after layer and gets finally compressed into ice. But in order to see those layers, you have to go underground. So let's check it out. It's a lot like looking at a very high-resolution photograph of how climate has changed in the past. You can really see the different layers in the pit. So this is 1 year's worth of snow accumulation, and there's a 2nd year's worth of snow accumulation here below it. And we can figure out what the climate was when that snow was deposited.
Researchers here are drilling cores of ice to investigate Antarctica's climate history. These ice cores contain bubbles of ancient atmosphere.
Real slow. Nice and slow.
Levels of greenhouse gases trapped inside the ice reveal times when conditions were cold or warm.
We're we're looking back about 100,000 years back in time, and that goes through the current warm period and the last glacial period.
But ice has existed here for millions of years. And since gravity steadily moves the ice sheet towards the sea, even the oldest ice can tell just part of Antarctica's climate past.
But the length of ice records only extends back to maybe 1 million years or so back in time. If you want to go further back in time than 1 million years, you have to go with rock records.
Finding the rock layers is a challenge on a continent covered by ice. As ice sheets grind across the land, they swallow up the rock layers that detail Antarctica's climate history.
There's been this erosional bulldozer, if you like, the ice sheet just bulldozing the rocks on the continent. There are no rocks left of the age we're after.
As an ice shelf extends over the sea, the warmer water slowly melts away the bottom of the ice, dropping stones to the sea bottom. So geologists are exploring places where ice has deposited them in layers of rock. The best sites are the ocean basins beneath McMurdo Sound. Here, marine life thrives in the salty, freezing waters of the sea. Over time, different sea plants and animals have adapted to changing ocean temperatures. Geologists with the Andrill Drilling Project will core into the seafloor rock layers to learn how long ice sheets have existed on Antarctica and how ice here has affected global climate.
Right now, Antarctica seems to be locked in a very cold climatic condition. That wasn't always that way.
Andrill geologists are not studying the ice itself. They're using sea ice or the ice shelf as a platform to support a rock coring drill rig. They're sending a drill through the ice and down nearly 1,000 feet of water to bore into seafloor rock layers. But drilling on ice is challenging. First, Andrill will drill on the McMurdo ice shelf. Although it looks like the ice is frozen in place, the ice shelf is in constant motion.
We're sitting on this floating body of ice, 600 feet thick. It goes up and down once a day with the tide, a meter or so. It's moving to my left at about 150 meters a year. One of the problems we have, if this ice freezes onto our drill string and it goes up and down with the tide, it's just going to rip it out of the ground all the time, and we won't be able to get any core.
So Andrill engineers created a hot water drill, a moving ring that shoots jets of steaming water to melt a wide hole through the length of the ice shelf. The hole allows Andrill to continue drilling as the ice shelf moves more than 70 feet during the 3-month drilling season.
And so what the drillers will do is deploy it on an angle and anchor it into the sea floor, and then the ice shelf will have moved over the top.
Then, Andrill will drill on thin sea ice.
We're standing right now in the southern part of McMurdo Sound. Seasonally, this region will break out. The sea ice that we're standing on will melt out.
Just 20 to 26 feet of sea ice supports Andrill's massive drill rig.
We have a drill rig that weighs 40 tons. That's before we add any drill pipe to it. So we add airbag flotation to compensate for the weight of the drill pipe that goes all the way to the sea floor, and we inflate that progressively as we add more pipe to it so that we can continue to drill effectively.
Andrill's drilling innovations on sea ice and the ice shelf will reveal a continuous record of Antarctic climate conditions since the continent plunged into a deep freeze. To learn more about Andrill's climate research, watch these episodes of Antarctica's Climate Secrets.
So amazing, the technology, the science and the technology that goes into this, huh? But, they've got it figured out. Long term, that ice is actually shifting, just like the Antarctic also. And seasonally, it puts out the shelves that then melt and drop whatever they picked up on the way to the bottom. It's just fascinating, the research that's going on. Yep. How to study ice, right? Yeah, well, those ice cores that they pull out, they have these sophisticated instruments where they can measure first. The first thing, I guess, would be to date it, date the layers. And even, I don't know if you noticed, but some of the photos, let me see.
striations on them.
Right, exactly. Even here, you can see there's a little brownish in between, right? That's all dust and particles that are falling on the ice layer. And this is one season. Then the next snowy season will cover that and deposit another layer of sediment and so forth. So there's this constant falling of particles on the ice sheet, and that has been going on over millennia. So those cores have these lines that can be dated year by year. They count down, just like the fellow who went on the ground under the ice. He says, this is 1 year, then this another year, and so forth. So they study those layers. And the first thing is to date them. And then within that particular time frame, they'll look at the air bubbles that are trapped there and measure the gases in those air bubbles. All right? And they can determine.
Point where you don't damage the ice and lose the gases.
Right. Well, it has to be kept, so those cores are also kept up there, right? Precisely because the ice doesn't melt. Like he said, the ice doesn't melt, the snow doesn't melt because it's always below zero, right? And so that becomes the lab itself. And they take advantage of the fact that it doesn't melt so that the bubbles are not lost. Yeah, it's just fascinating, the technology that's available today to do this kind of research. And all this precisely because of the concern for the climate change. All right, the third one then, so we looked at the Arctic, we looked at Antarctica, let's look at Greenland. And you'll see in Greenland, in my opinion, is the most dramatic of all three melting, at least for now, thanks be to God, it's the smallest of the three ice sheets. Okay? Very tiny compared to the Arctic. So,
when most people imagine.
Sorry, I just want to say this preamble because you'll see it in another video. Greenland, even though it's a small glacier compared to the poles, is significant enough to exert a horizontal gravitational pull on the water, which affects actually the sea level on the surrounding territory, okay? So I'm talking about the actual mass of ice on top of Greenland exerts gravitational pull because every massive body exerts gravitational pull, which is horizontal, perpendicular to the Earth's gravitational pull. And that has an effect on the coastline of the liquid water around it in the North Atlantic. You'll see what I mean in another little video.
When most people imagine the surface of the Greenland ice sheet, they picture a vast plain of blowing snow.
See the dust on it? See the dirt? Grayish?
In fact, it is a very wet icescape, and it's covered with streams and rivers and gullies all filled with rushing blue water. But the real shocker is that every single one of these rivers abruptly ends in a feature called a moulin, which can be a crack in the ice or a round circular portal in which all of the water flowing through the river penetrates down into the interior of the ice sheet. So what we've learned is that the Greenland ice sheet is not a featureless plain of ice. It's more like Swiss cheese, through which this meltwater is able to quickly and rapidly flow over the ice, enter into the ice, and then escape down at the downstream edge to flow to the global ocean.
And that flows into the Atlantic.
One of the most pressing environmental problems of the decades and centuries ahead is rising global sea level. And one of the leading causes of sea level rise is the melting of ice from glaciers and ice sheets. And Greenland in particular is the single largest melting chunk of ice in the world. We know from climate models and weather stations approximately how much melt is being formed on the surface of the ice sheet, but what we don't know is if that water is truly escaping the ice sheet to connect to the ocean and contribute to global sea level rise. So for the past 5 years, I and my dedicated students have been studying this problem using a combination of satellite remote sensing, using very high-resolution military-grade imaging systems, as well as intensive field work involving deployment of autonomous drifters and drones, tracking and studying one of the least understood hydrologic systems in the world. What our research shows is there is a clear and definite connection between climatological melting on the top of the ice sheet and the downstream outflow of water to sea level rise and floods in the rivers moving over the Greenland coast. There are two take-home messages from this research. The first is the discovery and a new appreciation for how significant these superglacial river networks are for quickly and efficiently removing meltwater off of the surface of the Greenland ice sheet and exporting it to the global ocean. The second is we now know that the fundamental assumption of these models, i.e. meltwater produced on the top contributes to sea level rise at the bottom, is in fact correct.
Okay. So Greenland, even though it's the smallest of the three chunks of natural ice, is the one that's melting the fastest. Okay. And that's fresh water, yes, because it's originally snow that has compacted and formed ice. And you may say, well, Greenland is an island, you know, it may lose its glacier. And the silver lining about that is that that island, Greenland, which it comes from the Norse people, right, for otherwise known as the Vikings, the Norsemen, supposedly were the ones who discovered Greenland. They call it Groenland. And they call it Groenland because there were vast green forests there way back 1,000 years ago, maybe a little further back. And the idea was that in Iceland and the other places of Scandinavia where the Vikings were living, the Norsemen, they had cut down all the trees already for their housing and for burning, for fuel, for food, for cooking their food. So they were looking for trees, all right? And they specialized in scouring the coast for driftwood. And even the driftwood was gone from Scandinavia and Northern Europe and the North Atlantic because they were using it for living. And so when they discovered Greenland, which was just a huge island of forest, they said, oh, Groenland. But now it's an ice sheet. So perhaps the silver lining of that melting of the ice sheet is that that island of Greenland will become green again. Eventually will become a huge forest, which could then be inhabited, right? However, it's not without its downside if Greenland actually melts because of this. Believe it or not, the horizontal gravitational pull of the ice. So again, think of it, any body that has mass, any matter, any material that has mass, we just call it a massive body. So a massive body is not something that is necessarily huge, is any object that has mass in contrast to energy, all right? So massive bodies, they all exert gravity, gravitational pull. It's just that the gravitational pull of this paperclip is insignificant compared to the gravitational pull of the Earth. Okay, but every massive body, including our own bodies, exert some degree of gravitational pull simply for the fact of the accumulation of mass. Again, the gravitational pull of the Earth itself is the largest gravitational pull on Earth. But there are others. As you can see in this, did I get it right? No, sorry. Let me pick up that here. So what I'm saying is that the chunk of ice on top of Greenland is exerting gravitational pull, horizontal gravitational pull on the surrounding water.
25 million years ago, a new species appeared on Earth.
Near a melting ice sheet, two opposing effects influence local sea level. A weakening gravitational attraction lowers the sea near the ice sheet, while at the same time, water flowing into the ocean raises it. To take a concrete example, imagine that the Greenland ice sheet suddenly collapsed into the sea. Globally, the meltwater would raise sea level by an average of about 22 feet. But relatively nearby, in places like Scotland, Norway, and Newfoundland, the disappearance of the ice sheet's gravitational tug on ocean water would cause sea level to drop.
Mm-hmm. Right. So locally, again, the water melting from the ice will form liquid water into the ocean, but all the oceans are connected, right? And therefore that water will dissipate, and the sea level rise is relatively small. It's like taking a few drops of water into a bucket that is full of water. It's going to change the height of that surface very little, just a few drops. However, locally in the near environment, the effect of that melting ice is more dramatic. See if I can get a on the coastline of the surrounding geography, because while that ice sheet is there, while that glacier is there in the middle of Greenland, it's actually pulling water in, right? Yes, exactly, toward itself. And so when that gravitational pull is gone, then that water is going to let go, right? And it's more dramatic. It's holding, it's holding the water in. I don't want to say artificially because it's a natural phenomenon, but it's not the same sea level as in other places, all right? It's a lower sea level. So these areas would then flood by the release of that gravitational pull. Maybe this one, just looking for a map. So here's Greenland. And what is nearby, well, Alaska, Canada, northern Canada. But this part of Canada is known as the Northern Territories, and there's very little population there, human population, because it's all permafrost, it's very drastic living conditions. It's in the Arctic Circle, actually, right? In the Arctic Circle. But it's more affected over here in Europe, Scandinavia, all right, Norway, Denmark, what's the other one? Sweden. And then Northern Europe here, again, Great Britain, Scotland, Ireland, Iceland. I think this is Iceland, all right? So those are all affected by the gravitational pull of this huge ice sheet here, which is above, remember, it's 1 to 2 miles above the sea level. So it's a significant chunk of ice. Okay, I don't know if you want to take a little break here. We're about halfway, a little less than halfway through some of the consequences of climate change. Shall we continue a little bit more, or want a break? Okay, let's take a break for a few minutes. And I brought some little goodies there you can have also. So let me pause recording. Okay, folks, welcome back. Now, we've been looking at all this evidence for climate change, right? Which is pretty substantial at this point. And there are three major consequences of this climate change. One would be the tropicalization of the Earth, because it's moving toward warmer climate, right? loss of the coastline because of the flooding. So we will lose coastline instead of gaining coastline in a winter recession. And also the impact on the species on Earth, an overall loss of biodiversity. Right? So these are three negative consequences of the climate change. Now, this little video has like a time series on ice melt throughout the world, globally, not just the poles and Greenland like we saw before. Okay, interestingly, this is produced from the business world because, again, climate change will have an impact on the economy, right, of the Earth. Oh, here we go. This time series has ice melt, the Earth would look like. Are seeing the coast disappearing, lakes whitening. Mountainous regions are less affected, of course. Coastline that is flat. Number of cities that are shoreline will be flooded. Africa. All of the coastline. Bangladesh. Asia. See how the ocean is moving in on flatlands, low-lying areas. Anybody guess? Because these are long, right? That's what it's talking about. The Amazon basin. North America. Now it's Canada, Ecuador. That's going up Mexico. Rio Cortez. Of course, there's a lot of continent range there, right next to the coast. But on the Atlantic, you're on the Atlantic. Huge Gulf of Mexico, right? All the way up the coast. Flooded. Several megalopolis there. That would be with the total melt. It's not going to be tomorrow. Maybe a few decades, a few centuries. We don't know exactly, because the rate is not linear either. It's an accelerating rate, and all has to do with CO2 and other greenhouse gases, not just CO2, methane, for example. Okay, so that's a pretty dramatic one. It's sobering. What we're talking about is this kind of effect. This is a photograph of Alaska today, right? Which could become tropical rainforest in the future with the tropicalization. Now, we also have evidence that this has happened before in geologic time with those cycles. What is one telltale evidence that Alaska, for example, has been tropicalized in the past? What do we find in Alaska that is very precious? A fossil fuel, oil, right? Petroleum. And petroleum is basically rotten forest, tropical rainforest. So we know that in the past, Alaska was also part of the whole tropicalization of the earth. It's just like the impact today because of the human population. All right, another aspect, so a tropicalized earth, we see would be pretty dramatic, especially loss of coastline. Another effect, independent of the warming of the atmosphere and the melting of the poles, is also the acidification of the ocean, because when CO2, which is a gas, mixes with water, it generates this carbonic acid, all right? And carbonic acid, like the word says, is acidic. And so it acidifies the oceans, which right now are slightly basic. Okay? So just to understand here for a moment, to review the pH scale, pH is the amount of acidity or alkalinity of a substance. And the standard that is used is just water, H2O. The scale goes from 1 to 14, but it's an exponential scale. And so a pH of 7, it means that is the hydrogen content in it, protons, goes from 0 to 14, but it's exponential. So 7 is 10 to the 7 hydrogen molecules or atoms, and that would be neutral, all right? So it's just translated, it's the exponent that is used as a single digit. The smaller the digit, right, below 7 is considered acid. In other words, less hydrogen. And the higher the digit is considered alkaline or basic. So again, 7 is neutral, and the scale is actually from 1 to 14. So acids are below a pH 7, and bases are above a pH 7. Right? The ocean right now is about 8.2. That's the average, so it's a little alkaline, right? It's one factor above neutral. What happens with acidification of the ocean, it changes the pH. It lowers the pH, right? So animals or plants, all the sea life that is accustomed to this kind of pH, a little on the basic side, will all be affected, all right? And there is estimated a gradual loss of sea life across the board, because that ocean is just all over the place, you know, and the sea creatures don't have an alternative. And part of that, dramatically, one group of animals that is very sensitive to the pH of the ocean is corals, which are salenterates, right? And that's one of the agents that causes this coral bleaching. If you've heard of coral bleaching, all right? Here is a healthy coral with many different colors, as you can see, and the colors are mostly from algae that live inside the coral. They're called zooxanthellae, all right? And that's what gives them the color, because these algae photosynthesize. And because they photosynthesize, they have color pigments on the reddish scale, brownish, reddish, etc. And that is what actually gives the coral its color, because the polyp itself, the coral polyp, is transparent, okay? It's alive but transparent. But when it gets those little algae inside the zooxanthellae, that gives them the color. And that is a sign of a healthy reef, because that algae is known as a symbiotic relationship where both species benefit. The coral gets the benefit of the photosynthesis, so a source of carbohydrates, And for the algae, it gives them a secure place in which to live, which is inside the actual polyp. Well, when the pH changes, what the corals do is they expel the zooxanthellae, they push them out. They push them out when the ocean acidifies, when the water acidifies, when the pH becomes lower, the coral are stressed. It's called, they go into distress, and the way to express their discontent is to expel out the zooxanthellae, all right? And that's called coral bleaching. And eventually, they have become so used to having that algae inside that eventually the polyp itself will die. And then what's left behind is just the skeleton of the coral, which is calcium carbonate, and that's why it looks white, all right? This, by the way, is not as hard coral. There's another type of coral that is known as soft coral, but the skeleton of that coral is not calcium carbonate, it's actually proteins. So that's why it's soft. Sea fans and sea whips, all those are soft coral. But the typical coral that we're familiar with has the skeleton that is hard, which is calcium carbonate. So when it bleaches like this, then this is a sign of a dying reef. And it's not just the coral itself, it's all the animal and plant life that goes along with that reef. Like we saw earlier, remember the community, which is populations of different species and so forth, and then you get an ecosystem. And the basis of that ecosystem is going to be the coral. So if the coral dies, eventually the whole ecosystem will die. There have been some reports lately about dramatic loss of coral in the Great Barrier Reef, which is one of the largest coral formations in the world. It's estimated that maybe up to 50% of the Great Barrier Reef is now dying, is bleaching. So here's an example, for example, you see the bleaching occurring right in the middle of the reef. It's a it's one of the highest biodiversities in the world, is the Great Barrier Reef, which is off the coast of Australia. It is huge, beautiful, spectacular, and here's another example of the bleaching, stack-on coral. These may actually be researchers that are growing coral in these structures. So I just noticed they're all the same shape. They look like little hexagonal spiders, right? And you see the brown part. This may be chunks of coral where they're growing it. They're trying to repopulate an area that had been bleached, maybe. Yeah, a lot of research on corals, because there are a sign, when there is a healthy coral, it's a sign of a healthy ecosystem all along, right? It's off the coast of Australia. Okay, so you can see that this issue of ocean acidification is another negative effect of increased level of CO2, aside from the global warming itself. Okay, the third one that I had there is a loss of biodiversity. So here's a little overview on biodiversity, but basically, in general, the tropical regions are the most biodiverse. And then as we move north and south from the tropics, it becomes less and less diverse. But the tropics, the tropical rainforest on land is the most biodiverse, where we have the greatest variety of species, plants, animals, fungi, and bacteria, and also in the oceans, all right? Which is typically where the corals are also, because they don't tolerate much cold, at least barrier corals. Individual corals do grow even in the northern Atlantic and northern and southern Pacific. So here's an explanation of biodiversity as a whole.
In 5 seconds, you can skip this ad. What you can't skip is climate change. But there is something you can do right now. Ecosia is a free search engine, like Google.
It's a professor explaining the biodiversity.
Hi, it's Mr. Anderson, and this is AP Environmental Sciences, video 35. It's on the loss of biodiversity. Way up in northern Norway is the Svalbard Peninsula, and on there, scientists built a giant seed vault. It's protecting the seeds of humanity, our crop seeds, into the future. They chose to put it there because it's protected against tectonic activities. It's really, really cold, and also as the sea levels rise, it's going to be protected as well. The idea was hundreds or thousands of years into the future, we could go there and grab seeds and then start growing those crops again. Unfortunately, we've already had to make withdrawals from that area. And the reason why is the war in Syria put a lot of these drought-resistant crops at risk, and so they've had to take more seeds out and they've moved those to Lebanon. But it does kind of get at this idea of the importance of biodiversity. Biodiversity is not only species diversity, but it can be genes, species, especially our domesticated crops and livestock, and then ecosystems themselves. And they have value. They give us our resources, and they also do these ecosystem services. And they're at risk. We're seeing biodiversity loss all around the planet. The causes are habitat loss, invasive species, climate change. We also have overharvesting, and then finally pollution are all impacting biodiversity. And so it's led to conservation. What do we do first? We have to figure out where that biodiversity is being lost. We have to figure out the conservation status of these organisms or areas. And then finally, we can pass laws and treaties to try to preserve a lot of that biodiversity. And so again, why do we need biodiversity? It's where we get our food. It's how we filter our water, energy, medicine. We all get that from our environment. And again, our environment also does these ecosystem services. They keep our climate stable. They decompose material once it's died. They pollinate our crops. And so we need biodiversity on our planet for resources and to do these services. If we define what it is, it's simply a variety. Variety at the genetic level, at the species level, and at the ecosystems. And so those genes that organisms have, once the organism is gone or the gene is gone, it's gone forever. It's extinct. Species as well. These are all the fruits found in a certain area of the tropical rainforest, but also we're talking about the crops that we have. And so I think it used to be we had around 8,000 different types of apples that were being grown, and now it's 100. And if you look in your own supermarket, it's way less than that. And then it's ecosystem changes as well. Once an ecosystem is gone, coral reefs, for example, you can't build that back again. And so what is causing this biodiversity loss? Well, when I was trying to come up with a quick way for you to remember these 5 things, I came up with this mnemonic. And so if you think of the biodiversity COP, and if you think of high COP as a way to remember it, if we put those in order, habitat loss is the first big impact on biodiversity. So deforestation, when we're cutting down those rainforests and planting crops. Right here we're growing soybeans. This is looking from above, where we used to have a tropical rainforest. We're reducing that diversity and we're replacing it with one simple crop. Invasive species, this is kudzu. It's a plant that was brought from Asia. These are the zebra mussels in the Great Lakes that they're really wreaking havoc. They came from the Mediterranean. We're also seeing climate change impacting biodiversity. So if we look at the polar bear, for example, will they go extinct? It's hard to tell. But if we look at all the areas where they used to do well, we're seeing a decrease in the optimal polar bear habitat. Also, over harvesting. Humans have been harvesting animals for a long period of time. The dodo is extinct because we killed all of the dodos. And we're also seeing over harvesting now, especially in our aquatic systems. And then we can have pollution. Pollution's impacting the environment as well. So if we look at that Deepwater Horizon explosion, that led to an oil spill, which is impacting biodiversity in the Gulf of Mexico, and it'll take us years to figure out how that impacts it. Now, this has been going on for a long period of time. Extinctions are a part of nature. And if we look back through the fossil record, we've seen 5 major mass extinctions over time, and they have different causes. But most scientists are pointing to right now as the 6th mass extinction. This is mass extinction caused by humans. We're seeing extinction rates that we've never seen before, biodiversity loss that we've never seen before, and its cause is us. And so how do we solve this problem? Well, the first step is to identify where the problem is. And so the IUCN, International Union for the Conservation of Nature, has been around for over a half a century, and what they've done is come up with these different statuses. Extinct in the wild would be one where we maybe have them in a zoo, but they don't exist in the wild. Then we have critically endangered, and vulnerable. Then we have near threatened, and finally areas of least concern. And so if you go on Wikipedia, you you can look up any animal or any plant and it's going to tell you its conservation status. So for example, the whooping crane are endangered. The California condor is critically endangered. Humans, you can imagine, are an area of least concern. They've then created this red list where we look at how many of these species fall into these threatened or these red categories. If we look at mammals, almost 20% or over 20% are in this threatened kind of an area, and amphibians are really at risk. And so what do we do? Well, what we can do is pass laws. So in the US, we passed the Endangered Species Act in 1973 to protect species and the ecosystems on which they depend. And so it essentially is a list. So bald eagles are a classic example that were added to the endangered species list. And so there, I think, were around 500 breeding pairs in the lower 48, and now there's over 10,000. So once they recover, we remove them from that list. Grizzly bears were added. Their population is coming back. In Montana, there's a big debate right now over do we remove them from the list or not? But it also has to be balanced with human resources as well. So logging, for example, can impact certain species that are going to be found on the endangered species list. We've also seen global changes. The Convention on Biological Diversity in 1992, all of the green countries here signed on that biodiversity is important, it has an economic import, and that we're going to try to protect it. But again, it's not legally binding, and so we're still seeing huge decreases in biodiversity. And it goes back to the first thing I talked about in this class, the idea that the planet supports society, but society is driven by economics. And so we're never going to see decreases in biodiversity loss until there's an economic incentive or a way to do that. And so did you learn the following? Could you pause the video at this point and fill in the blanks? Well, let me do that for you. Biodiversity has value. It's a variety in the genes, species, and ecosystems, again, especially the domestic ones that we need to survive. That loss is caused by high COP, so that's habitat loss, invasive species, climate change, overharvesting, and pollution. And then how do we solve this? Through conservation, we figure out the status of those organisms or maybe those ecosystems, and then we start to protect them through laws and treaties. So that's it, and it's also the last of the videos on AP Environmental Sciences, so I hope that was helpful.
Okay, fast talker, but it gives a good overview, right, of that biodiversity and the rate of loss. That's the problem because, as I mentioned early on in the video, every species is due to become extinct sooner or later, all right? It's just that that happens in geologic time. We're seeing, and that's what is known as the background extinction rate. But now we're seeing, again, a geometric increase in the extinction rate of species around us. Most of them are small, so we don't really notice it on a daily basis, but a few are large animals. And the ones that are getting most hit right now, in general, the large groups are the amphibians and the insects. And it's mostly interesting that it's mostly due to habitat loss, not necessarily climate change. It's one of the factors, as you mentioned. But the biggest impact is really loss of habitat, where the species will live because of either agriculture or urbanization. Okay? So, well, maybe I'll skip this one. Let's move on. It's another little video that you can see. It's just a news clip from a couple of years ago in France. So you notice here's human population in purple, right? There's that transition from the lag phase to the log phase. And then you can see how the extinction rate also parallels that curve. If we draw a slope, the two slopes will be very similar in shape. But the biodiversity, again, is impacted more, loss of that biodiversity with the increase in human population. And it stands to reason because, like I say, we have to live somewhere and we need to grow our food somewhere, right? Well, that is habitat, wild habitat that is lost. Again, I can use the campus for an example because we're all familiar with it. You know how we have an effort to conserve the forest, what's left of the forest, which is about 15 acres more or less. But this campus actually has 140 acres. And before the university was built here 60 years ago, it was all forest. It was undeveloped. So now we're down to 10%. So 90% of the original strand here, just 60 years ago, the 1960s, was all forest. And now we're down to 10% of the original forest because of the university, right? So at least since we're going to, that's our footprint, by the way, on this plot of land has been that 90%, and we're desperately trying to preserve that 10% so that it's not wiped out. So the least we can do as a payoff is teach about conservation in our university, right? Because we are living example. All right, here's a little bit of what I was mentioning. How do we get that temperature? You see the wiggle line is measured by instruments down to the 1960s. So it's not that long ago. And it's wiggle because it has more noise, precisely because this is averaging thermometers measuring the weather over yearly cycles, okay? So it has more noise, that's why it's wiggly like that. But the blue line, the smooth blue line, it says from ice core samples. So that's more smooth simply because it's more average, it's not as accurate. It doesn't have as much noise, but we can always look at the slope anyway. And when we connect the two, so what it's saying is that before the 1960s, we just didn't have instrumentation that was reliable enough to measure the atmospheric CO2, all right? And then the temperature that parallels, if we were to draw a slope on this green curve, it would pretty much parallel the CO2. So all this is basically saying that the CO2 rise is the main contributor, at least right now for the past 100 years, of increasing temperature of the atmosphere. All right, enter the UN because they have been having, the United Nations has been having a conference or convention on global warming and climate change for many years now. And they're trying to track this intensely. This is just their site here for a moment. Okay, and they have something called IPBES, which is the Intergovernmental Science Policy Platform for Biodiversity and Ecosystem Services. So that's the long phrase for it, the acronym IPBES, to try to get governments to sign into and to buy into the protection of biodiversity and ecosystems throughout the world. Of course, the issue with this is that it is on a voluntary basis, right? They cannot enforce any kind of taxes or fees or fines on this. It's all by volunteer of the countries participating. In the United States, something positive that happened is essentially the National Park Services, the National Park System, which was thought of by Teddy Roosevelt. He apparently was an avid hunter himself, okay? And he appreciated nature and the wildlife. So he came up with the idea of a National Park Service that would be preserving areas, geographical areas of the United States for future generations, indefinitely, all right? So the whole issue with National Park Services is that these parks will not be developed into urban areas or agricultural areas. They will be preserved as they are. Typically, it's large acreage. And one of the characteristics to qualify for a national park is that it's a unique ecosystem. So for example, we have several in Florida. We have the Everglades on land, And then we have Biscayne National Park on the water, which is mostly reefs and grasslands on Biscayne Bay, all right? And so those two ecosystems are unique. They don't exist anywhere else in the United States. And that's one of the characteristics for qualifying. The first national park was Yellowstone, which is a huge caldera, essentially. It's a huge caldera of a volcano that is extinct now, but it can blow up anytime. And that's why it has those geysers and the steam fumes coming up and the hot springs and all that, because underneath is the magma fairly close to the surface. So when the water percolates all down there, it boils and steams up, and then it shoots out in these geysers. Like, for example, Old Faithful, right? I don't know if you've heard of Old Faithful. It's one of the geysers that is in Yellowstone. I had the privilege of visiting there with my brother and sister-in-law several years ago. I'm looking for Yellowstone. Because they used to live in Colorado. And one year, they took me to visit Yellowstone, which is just beautiful. It's got the grizzly bears, the bisons, and these hot springs. It's impressive, especially if you go in winter. You see the winter snow and you see all these hot springs fuming and boiling. It's pretty dramatic. But especially key, I was looking for a map. Yeah, it's a huge caldera of a extinct ancient volcano. Anyway, that was the flagship national park established in the US, and now there's a whole system of them, right? They're maintained by the National Park Services, and some of our taxes go to maintaining that. Okay, so back to the UN and some international treaties beginning in the 1960s. There's a conference in Sweden on human interaction with the environment. Then about 10 years later in Stockholm, there was another conference on humans and the environment. And the result of that was the Stockholm Declaration. So these become kind of flagship documents and groundbreaking, right? Paying more and more attention to the protection of the environment and encouraging countries of the world to establish, for example, a National Park Service in each country. I had some friends that just came through Miami the other day, and they had been in Costa Rica for a few days. Costa Rica has devoted large portions of its own country to parks, and they have actually generated an entire industry and an economy based on tourism. It's called ecotourism. And people go there to visit the wildlife that is in Costa Rica. So I have a lot of national parks, and large parts of the country have been devoted to that. So they made an industry out of it, ecotourism. It's known worldwide. Unfortunately, these things get politicized also, and there are various competing interests on it because not everyone's going to look at it from the principal perspective. Sometimes it's a lot of utilitarianism that is coming into these areas and will be used as some kind of a political leverage or ideology to move certain ideas through society. So it's not perfect, but there has been an increasing attempt to preserve biodiversity throughout the world. And one main way of doing that is preserving natural habitats, right? So things like urban forests have become more prominent. Inside, like the word says, urban forest is a natural ecosystem of wildlife, but embedded within cities. That the rest of the city is just urbanized, all right? And now there's a further concept from that, even at a smaller scale, is what is known as microforest. And a microforest could just be the front yard or the backyard of a house or a neighborhood or maybe one city block that is dedicated just to allow the native vegetation to come back up. And that will bring biodiversity to the area. Birds and insects and all their animals will come into that area and colonize it, because now they have a natural, little tiny natural habitat. It's like an island of wildlife. It's also called microforests, okay, in the middle of urban areas. So in principle, any house that has a yard or a garden or something like that could become a microforest. The idea is that the native vegetation will be encouraged to grow there, which will increase invariably, that will increase the biodiversity of that local area. Again, the Rio conference in 1992 in Brazil was also another watershed for protection of the environment. And from there, eventually developed a yearly and annual conference, which is this COP. The COP is a conference of parties, right? It stands for Conference of Parties. And it assesses, like it says here, the progress in dealing with climate change and loss of habitat throughout the world. And since the vast majority of the countries of the world are participating in the UN, it's close to 200 countries in the world, and I think about 195 of them belong to the UN, all right? So as you can see, these conferences have been going on every year to assess what is the impact of climate change and loss of habitat up until last year. And then in 2020, there was none because of COVID. It was canceled last minute, and it's supposed to take place this year. Yes, UK and Italy, I think, were co-sponsors. Oh yeah, so after the Rio protocol, then this other one in Tokyo, Japan, was about 5 years after the Rio conference, was another watershed in the area of preservation of the environment. 192 participants, almost practically all of the nations of the world. Then the 2015, the famous Paris Agreement, right? They're focusing now on keeping the atmosphere from not rising more than 2 degrees centigrade, all right? Not more than 2 degrees centigrade. It's actually a very ambitious goal. It would sound humble and you know, not very ambitious, but it is actually ambitious because that CO2 keeps shooting up, and therefore to maintain it within an increase of 2 degrees is very challenging. All right. The 3 main polluters of CO2 in the world: China, India, and the United States. So for somewhat different reasons, in general, China and India is because either they don't have regulation or the regulation is not enforced. We have regulation, it is enforced, but our industry is still heavily dependent on fossil fuels because it is the cheapest fuel still available, as we saw from the energy lecture a couple of weeks ago. And that's the challenge, because we are driven by a market economy. If it's not economically feasible, the industry is not going to change and take a loss. So it has to be made economically feasible, like the professor was explaining for the biodiversity thing. All right. So for example, in the Paris Agreement, these are all the signatories of the world except Syria, United States, and Nicaragua. Not in good company, frankly. Politically speaking, not in good company. But of course, with this current administration, one of the first things that Joe Biden did, President Biden, was to declare that we're signing back into the Paris Agreement. We'll see how it goes. It has economic impact also, but at least that's the talk, all right?
I was still in Peru when they have the COP20.
Yes.
And it's a big event because they
Yeah.
only have like political person of the same group
Right.
Also, they involve the community.
Mm-hmm.
They have like a ferry where they present also like resources or
Yes.
what is the world working on to try to solve the environmental projects. And
Yes.
they have like a lot of education for around
the local community and regional. Yeah, what is it done in?
Universities, and they have
Right.
like volunteers to organize
Mm-hmm.
an event that it lasts like 2 weeks.
Yeah, it's massive, huh? It was done in Lima?
Yes.
In Lima, right. Exactly. Yeah, it's massive. And they try to involve the local community and a lot of social activism.
Yes.
Huh? It is. It's huge. It's a big to-do, really. The COP thing is a big to-do, and it has its own synergy, right? And so it's moving forward. We have to focus on what's positive about it.
To attend, if you sign up,
Mhm.
they let you go into some of the round tables with the,
Yes.
authorities.
With the members, member states. Yeah, observing. You cannot vote, but you can observe how the discussions are going on. Yeah, that's the whole thing is they try to do transparency on these events because it involves the world. Mhm. Yeah, it's very exciting. So you actually participated a little bit in some of it? Yes? Mm-hmm. Oh, yes? Wow. Yes, it's huge. It's huge. Yeah.
Has it ever been here in the US?
Not in the US. No. No. Yeah. It's a challenge, but yeah. So maybe someday we can host it. All right, this is another video that again is a little sobering because, so before a little explanation here, this is known as the Human Influence Index. Again, it's from the NASA website, and here's the reference down here, all right? But basically you see the scale here from low influence to high influence. They have a scale of 64, I guess it's some kind of a doubling because 32, 16, 8, 4, 2, right? So maybe it's a doubling scale, what they have here, I don't know. At any rate, the highest score is 64 on this scale. And that's the dark red or brown, all right? Which correlates with high density population. And the lowest is 0 or green. For example, here, don't be deceived because this is the Sahara Desert, which doesn't look green. You know, it looks sandy color because it's a desert, but on the scale it's green, just like, look at this, northern Canada, Greenland, which is not inhabited and doesn't have this kind of forest, all right? It's ice. And Siberia, which is a huge coniferous forest back here, and tundra. But the green is least impact of human influence on the world. Okay, so this one is on population growth. It's a time lapse and it moves quickly. So we have to be attentive to the little, I think they're yellow dots that appear. Right. So they'll be placing little yellow dots as the population of the world increases throughout history. And also, periodically, they will show whatever civilization came up in that time of history. So they'll show, for example, ancient Egypt, and then the Roman Empire and the Middle Ages and so forth, all the way up to current times, how the world has been populated by humans.
An environment is a system of living things. The Earth is our environment. The capacity of our environment to provide space.
Capacity. So whenever we hear capacity, we think of the carrying capacity, right? What is the carrying capacity of the world for the human species? We just don't know. Precisely because of artifact. We build cities artificially, and we grow food also artificially.
Produce food and to supply energy are all limited. Humans thrive on less than 17% of the Earth's surface, and only about 4% will grow crops. We depend on these limited resources for our survival. Yet we are increasing our population as if they were infinite. This fact is at the core of our environmental problems. On this map, we'll show population growth from the year 1 CE to the present and project our growth into the year 2050.
By the way, 1 CE is Christian era. So the past 2,000 years, essentially, the first year of the Christian era, moving forward for 2,000 years and into 2050, so 30 years beyond our current time. Here we go.
Population concentrations will be indicated by dots, each of which will represent 1 million people. In areas where people are spread out and don't live in concentrations of 1 million, dots are placed in the middle of their approximate range. Historical references will be provided by images and text at the bottom of the screen.
That just has the heartbeat going. And, you see, each yellow dot is 1 million people, right? It's the year 130, 140, coming up to the 2nd century, Christian area. Mostly Asia, India, and Europe. Third century, the dots in America. Coming up to the 500s, 1/4 of the way, more or less. Islam in the Middle Ages, lower Middle Ages. So where the original dots were, that's not going to get less dense, it's just going to increase in density, and new yellow dots appearing. Still mostly in Asia and Europe, a little bit of Africa, very little in North and South America. After the year 1000, this is Mesoamerica, the pre-Columbian empires there, Aztec, Toltec, Maya, Inca, South, here's Inca. See that India by far is the one that is the peninsula here of India, right? The most densely populated, especially up north here. What is the big mountain range there? Himalayas, right? So it's keeping the south 1800s, Southeast Asia, China. Everything's firing up. Exponential growth rate for sure. Hundreds, thousand, everything's lighting up. Right? That's it. Okay. Hold on. So let's look at that for a moment. Yeah, it's pretty dramatic. But each dot represents 1 million people. it's a projection, but it's a projection that is based on tremendous amount of data. If we continue with the same rate of increase up to 9 billion. So this projects it 1 billion beyond of what, right now we're at 7.8 billion more or less, just under 8 billion, all right? So in 30 years, another billion estimated. So that's how it would look like. Okay.
Our population is expected to grow to 10 billion by the end of this century. Yet the Earth's size remains the same. Slowing human population growth and lowering our use of natural resources are key to reducing the impact we have on the planet. Through the decisions we make about our lifestyles, our numbers, and our consumption, we can all help preserve the health and beauty of our home.
Okay, so it's a very dramatic little video, just 6 minutes, showing the rate of increase, but definitely going into that lag phase. Now, what's been reported in the past few months is the dramatic decrease in population growth in mostly the industrialized world, a big part because of combination between contraception and abortion and just couples not having children, period. They don't want to have children. And so that is dramatic and will put a kind of a wedge into that growth rate, but it's still occurring, like I say, mostly in Europe and North America. So moving forward, the challenges are big, but we have to work at the local level, right? Because most of us don't have a worldwide influence. We work at the local level to try to promote a responsible lifestyle, of trying not to consume as much, trying not to use as much single-use plastics, things like that, recycling, just have a general conservation mentality, try to preserve the environment. Now, one person who does have a global influence typically is the Pope, because Catholics are about 1/5 of the world's population, about 20% more or less. And beyond that, many people listen to the Pope, what he has to say, even if they're non-Catholic or non-Christian. So the encyclical, as I mentioned, it's a document that is written by the Pope and is the highest level of authority, at least in the Catholic Church. And the one encyclical that Pope Francis wrote early on is this one called Laudato Si, which is old Italian. It means praise be, and the continuing of the phrase is praise be to God for Brother Sun and Sister Moon and Mother Earth. It's a poem that Francis of Assisi composed in the Middle Ages to nature, right? Francis, we know, the saint of Italy, was a great lover of nature. And so Pope Francis chose his name precisely based on that Italian saint, all right? Because his name was Jorge Bergoglio from Argentina. And so the popes do that. They change their name when they're elected pope to a saint that inspires them. And the saint that inspired Francis is, Pope Francis, is Francis of Assisi. So he writes the first encyclical in the history of Christianity dedicated to the environment. That's the name of it, Laudato Si. The subtitle is Care for Our Common Home, which says a lot, right? Care for our common home, meaning that we all live in this one planet. And he wrote it in 2015, which is now 6 years away. But at that time, when it came out in the summer. So it had the publication date of Pentecost of 2015, but it was still not available. They were doing some final tweaking on it. And it finally became available in the summer of 2015. I must say also that encyclicals in the Catholic Church used to be small documents, 10, 15 pages. But now they're getting into 100 and 200 pages, so they're actual books. And certainly there's a lot of detail there and technical aspects, and the Pope is not fully competent in all those aspects, so he has a very large body of consultation, both on the scientific community, sociologists, theologians, economists. So it's a whole team of people that advise the Pope whenever they write an encyclical, all right? And these documents tend to be very, very profound and broad range and long impact. So it was written in 2015, and I became aware of this first encyclical dedicated to the environment in the history of the Catholic Church. So together with some colleagues here at the university, we put together a conference, an international conference on climate, nature, and society, all right? And we did that by 2016, so by the following year. In fact, we invited it was a 2-day conference, Thursday and Friday, and Thursday was devoted to the scientific evidence for climate change, right? And Friday was devoted to some of the social impact of that climate change. And the keynote speaker was this cardinal called Cardinal Peter Turkson. And Peter Turkson was the writer of the encyclical for the Pope, all right? He's it's called the convener, and he's the one who wrote the draft, essentially, for the Pope with a lot of consultation. At any rate, we filmed and we videoed all the talks. It's 3 talks on Thursday, 3 talks on Friday. And just to show you a little clip there, they're all available. There's Cardinal Turkson. Yeah, this is going to be the first one. Now, this is Richard Muller, who is an astrophysicist from MIT. No, I'm sorry, UCLA, who was on the scientific side. He's the one that gave us the big picture on climate change. But the last one, let me see. Oh. Anyway, let me go back here for a moment. Because, yeah, here it is. That's Cardinal Turkson. Just
well, thank you, Rosa.
Rosa is Rosa Patti. She's one of the professors here at St. Thomas. She's a lawyer in the School of Law, and she is a member of a pontifical council of the Vatican that is headed by Cardinal Turkson. So she was able to invite him over, and he came in February of 2016 to give us.
I think it's so very easy for all of you to understand that being a member of our council, he had to do this so we don't fire hair from our council.
Yeah. Okay. So anyway, there's a talk, there's a link. You can listen to the talks as your leisure, perhaps through the rest of the summer, since this is the last lecture. But this is what happened in 2016, just 6 months after the encyclical was published, thanks to the collaboration with a number of colleagues here at St. Thomas, all right? And by the way, from the start, we wanted to make this available also to the young people. So our goal was to have at least 50% of the audience be high school students. And so we went into the local high schools and invited the students, and we even provided bus and lunch and everything for them so that they could come and participate in the conference. Because I think that the young people especially need to be exposed to this, right? Because they're going to be the future generation of adults to take decisions in society about environmental issues. So that was done in 2016. And then 3 years later, we organized a second one, which was, so one of the groups that was sitting in the audience, just listening to the conference in this first one, was a team called the Nature Conservancy. I don't know if you've ever heard of them. But this is an international group that is involved on preserving the environment. That's their website. Okay. And so the Nature Conservancy is just like the word says, they are an international group that is focused on preserving the natural environment. And they're involved in many countries of the world. They have projects, for example, in the Caribbean islands, they have projects of growing tilapia in some of the lakes and rivers for feeding the population. All right, just as an example, in urban areas, if there's a river that goes through a city and it's contaminated, they will work with local officials and the people of the place to try to clean up that river. And they've done that. I know in Denver, for example, there's a river that goes right through the city and it was polluted and so forth. And they clean it up and now there's fish and wildlife. And they did like a little easement on each side of each bank of the river. So now it has walking pathways and it's a little bit of nature going right through the city of Denver. It's just one example. So they're very focused on conservation and help out local communities to restore whatever is contaminated. It turns out that the Florida representative of the Nature Conservancy was in the audience on the first conference. And then a few months later, I got a call from this lady who was up in Tallahassee saying that she liked the conference a lot. And if I was planning on doing a second one, that the Nature Conservancy would be interested in sponsoring it. So that was fantastic. I said, absolutely, let's do this. So we partnered and we joined forces. And 3 years later, we produced a second one. And this second one was based on, they wanted to see what faith communities were doing about preserving the environment, okay? And so this one, again, was 2 days, Thursday and Friday. It's in the format, but we had speakers. There it is, the Second International Conference on Climate, Nature, and Society, STU, and the Nature Conservancy. All right, and there's a link somewhere. Okay, schedule of events. So then we had all the speakers, beginning with Archbishop Wensky was one of our keynote speakers. And then all these people who are different faith communities. Some are Catholic, some are Protestant. We had a Jew also, a rabbi who gave a powerful talk. He's from Palm Beach, I believe. And we also had a Muslim representative. So it was truly interreligious. There she is, Nadia Ahmad. She's also a lawyer, and she represented the Muslim community on what they're doing on conservation. So it was all focused on faith-based efforts to preserve the environment. Here is Mayor Gilbert, who's the mayor of Miami Gardens. So we have quite a panel. Yeah, it's also recorded. It's down here. Okay, so you can go here. Oh, yeah, so what happens here is you have to scroll through all the first videos. Just go to the end, and the next, and the next, and the next, and then it'll connect.
Okay, without further
they're all hooked up, okay? So just keep going forward, talk after talk, until you get to the second batch, which is all these fellows. And we even had another representative from the Vatican, Tebaldo Vinciguerra, who belongs to that Pontifical Council for Integral Development, where Cardinal Turkson is the director, all right? So that's why he made the conference international in the sense that he was coming from the Vatican to give a talk. We had some people, for example, this fellow, Harjit Anand, is the director of Miami Water and Sewage Department. So we have some local representatives on environmental issues, all right? Dr. Kirkman is from UM, and also on, so he was kind of the scientist on board, talk about, bring us up to speed on what's happening with environmental issues. The Rosenstiel School of Marine Biology, which is in Key Biscayne, right? And so forth. So this lady, Irena Baguet, for example, she has been hired now by the new mayor, it's the mayor of Miami, Daniela Levy Cava, right? She hired Irela Bagué and started a new position for her as a director for Biscayne Bay, because Biscayne Bay is contaminated and it has a sewer plant next to it and so forth. And there's been a lot of dumping over the decades into Biscayne Bay. So she's now in charge of getting Biscayne Bay cleaned up. So a lot of people are influential in our community, right? And they did the second one. So now, beginning to think, some people have asked me, when is the third one going to happen? We're 2 years away, so if we follow this track, by 2022, we should have a third one coming up. And what I like to do is something with, the environment and the economy, all right? And use profit from the new building that we have, the School of Business, right? With a brand new building that is looking into the forest, right? As we're clearing it up and so forth. So I'm talking with some people over in the business school, some colleagues, to see if they want to jump on board and do a third one on the environment and the economy, especially post-COVID, right? How to get people back to work and how can we synergize to see. Of course, during 2020, there was one positive thing about 2020, maybe the only positive thing. Exactly. It's a big dip in CO2 because of the shutdown throughout the world, all right, the lockdown and all that. And so cities like Beijing, for example, that were totally covered with smog. I don't know if you remember the Olympics at Beijing. There was a big cloud of smog, right? And let me see, I'm probably spelling it wrong. Pollution. Yeah, Olympics air pollution. I mean, these are images that were, that's the nest egg that they built at the stadium with state-of-the-art engineering. So you can see that. And now look at this, how it's looking in 2020, right? It's just amazing. That's the same photo there, you can see. So there was some positive things about the COVID, but now that lockdown is over, it's creeping back up. And therefore, let's see what we can do with regards to the environment and the economy. Anyway, those are my thoughts. So that brings us up to speed. There's a little saying, think globally and act locally, right? Because these issues of climate change are global. Again, it's focusing on that anthropogenic factor, the footprint, the human footprint on the environment, because we have to live somewhere, but how to minimize our footprint and make it more eco-friendly. You can, for example, just plant plants around your home, even in pots. If you don't have too much of a garden, of an area, you can keep them in pots, but that increases the plant biomass, which is absorbing CO2 just passively all day long. Right? So having plants is a little contribution to diminishing that 4 gigatons of extra CO2 that we have on the annual budget. Okay, folks, that's it. And questions, comments? All right, well, thank you very much. That's all I have for this course now. So thank you once again for participating. We'll take a little break for the rest of the summer and gather back in the fall. It will probably be around the first week of September because we don't need all 16 weeks for the material that we're covering in the fall, all right? But I do encourage you in the meantime to continue working on the internship hours so that we accomplish that. Okay, and also you're welcome to some of the snacks there as you wish. Let me stop the recording and start downloading.